Hello everyone, thank you for joining our presentation today. My name is Umutcan Kılıç. I'm a master's student and research assistant at the Boğaziçi University Civil Engineering Department. Today I will present you our experiment study on the evaluation of different ultra-wideband tech placements on construction workers for enhancing safety. So this will be my agenda for today. And our research started with a simple question: how might we determine the optimal placement of these tags in order to ensure reliable, accurate, and continuous real-time worker tracking in construction environments? So when we check the background of this problem, we see that construction industry is very hazardous, and despite technological advancements, there remains still some problems in terms of this accident rates. So real-time location and systems emerge as a viable solution to lower these rates. And when we check the state of art, we see that the technologies involve usually computer vision, GPS, RFID, and ultra-wideband. So all of these technologies have their own unique benefits and disadvantages, and having high precision real-time data and being able to perform significantly well in complex indoor environments, ultra-wideband excel among the others. But there are some key issues. So the data quality and accuracy really depend on non-line of sight conditions, and tag placement is a critical factor here. So signals are blocked or absorbed by the human body or the surroundings. So when this blockage is caused by the human body and the human body itself, so like if you have a tag on your body and your body itself causes the signals to interfere, then this is called body shadowing, and this is caused by moving lips and body posture. And there has been no comprehensive study to test how different body tag locations affect the data quality. So our motivation is to determine the optimal tag placement for minimal signal interference and maximum tracking accuracy, and to support the integration of this technology into existing safety gears. So we carried out a controlled walking experiment using an ultra-wideband based real-time locationing system. We developed our system using a commercially available kit, and we had 6 participants in the experiments, and we placed 4 tag pairs on the bodies of these participants. So in this figure you can see the locations of these tags. So we selected these locations based on the availability of existing safety gear, such as the helmets or safety vests. So we had 2 experiment routes perpendicular to each other, and each participant completed 60 passes. And we had a 4 anchor setup placed in XY rectangle with different heights to improve trilateration accuracy. And we collected the data at 10 Hz using a Raspberry Pi 5 serially connected to a listener tag, and we also recorded videos at 30 FPS for pre-processing. So in the pre-processing, we use these video footages to get the exact timestamps of valid walking intervals, and based on these intervals, we filtered our data. So this is a CAD drawing of our experiment environment. So you can see our 2 perpendicular walking paths and the locations of our anchors. And this was our bundle for data collection. So we carried out some statistical analysis on the data collected. So first we checked the data completeness. Then we checked the measured center locations with the theoretical center locations using t-test, and we also compared the variances across the axis to see the performance of this setup across the axis using f-test. And lastly, we calculated the mean absolute error and standard deviation values. So based on the video footages, we identified the amount of valid passes and the duration of each pass. Also, we calculated the average walking speeds, and when we compared the speeds, the walking speed during the experiments was relatively close to the preferred walking speed of humans. So based on the video footages, we expected to have some amount of data based on our data collection rate. And when we compare the actually collected data, we see that some tags, for example, the tags located at the head has almost 100% data collection rate, but this rate changes for some other tags. So when we compare, when we look at them as pairs, so when we check when both tags of the pair was able to collect the data, we saw that head-mounted pair performed significantly better than the others. We had 99% data collection rate, but for example, knee-mounted pair was only able to collect less than 30% of the time. So imagine the experiment took 100 seconds, so for 99 seconds, the head-mounted pair was able to collect data, but this was like almost 30 seconds for the knee pair. And our key takeaway from this finding was that only head-mounted pair has a very significant data collection rate, and the lower placements are significantly affected by non-line of sight conditions. So we also carried out some t-tests, and we've seen that only the head-mounted tag pairs show no significant difference from the theoretical path, but the others show significant difference, meaning that only the head-mounted tag pair accurately reflects the worker's walking trajectory. So these were the results for our t-test. So in the f-test, we compared the variances of absolute errors between the axes to see if the system performed well in both as well in both axes, but for all tag pairs there was significant differences of variance across the axes, meaning that the anchor layout and walking direction greatly impacts the measurement accuracy. So this was the results for our f-test. And lastly, we calculate the mean absolute error and the standard deviation values. So the head-mounted pair resulted in the lowest minimum absolute error and the second lowest standard deviation on the gray route. So we have 5.7 centimeters of absolute error and 4.5 centimeters of standard deviation. And the results are similar in the red route. So when we compared our findings with previous research, we saw that the minimum absolute errors are comparable to W78 et al.'s study, where they used this technology to track construction machinery, but we experienced some higher standard deviations, which might be linked to the human walking factor. Also, we showed the impact of non-line of sight caused by the human body, and we also showed the potential of this technology in worker tracking, and also its sensitivity to anchor setup. So this was a systematic evaluation of ultra-wideband tag placements on the human body, and as far as I know, it's one of the first studies to ever do that, and we shown that the head-mounted ultra-wideband tags perform significantly better than the others. So in short, this study can be seen as a practical reference for integrating this technology into construction safety workflows. And we have seen that tag placement critically affects the tracking performance. And we have shown that the head-mounted tag pairs seems like a viable option if the deployment of such a technology is considered. But anchor configuration still matters. So when we check the European standard for helmets, we see that the weight of each helmet is around 300 to 500 grams, and each ultra-wideband tag is 35 grams, including the battery. So a pair is 70 grams, and with inclusion of these sensors, the helmets are still in the given range, meaning that the practical integration is feasible. But tag stability, comfort, and personal protective equipment compliance and the test performance of workers should be considered. So our study has some limitations. So we carried out our experiments in a controlled indoor setting, and we allowed only one participant to be present in the experiment. But in real life construction sites, we have multiple workers working in proximity. So also we have limited sample size, and we were only able to check one anchor configuration. So in the future work, these findings must be validated in real construction sites, and ultra-wideband accuracy should also be tested for complex movements. So we only considered very simple walking scenario, but in real life construction sites there are also crouching climbing stairs, etc. And the effects of alternate anchor layouts and additional anchors must be also considered. Lastly, sensor fusion, combining different sensors such as GPS and ultra-wideband also should be considered for more comprehensive and robust worker tracking. So these were our references. Thank you for listening. I will be happy to answer your questions.